So I turned back the that equilibrium homework. I still got to get the moment homework back to you. Now, the one thing on the equilibrium homework on that 2D, two-dimensional one, right there, the angle of that cable is going to be 45 degrees. And the reason is that you've got an equal force pulling it to the left and pulling it down. So to hold equilibrium, the force in that cable, I think, is 294. Is that right? I thought it was 294, if I remember right. So what that means is you've got, if you look at D there, these forces are equal to one another. So they're both 294 newtons, I think. 30, yeah, that's about right. So for equilibrium, and I won't go through all the formal stuff on this, but that cable is gonna have 294 going both directions. So the components X and Y are balanced in that cable. So what that means is the cable will go at an angle that reflects that, which is 45 degrees. All right. Now, one thing on that, when I was going over that, some people just wrote down 45 degrees, and give me something on that. You know, I always need to know how you get to an answer. I just don't want the answer. I want how you got there. Now, maybe you did some equilibrium analysis, and maybe you just said the forces in the X and Y direction are equal. You know, you could have written a little statement or whatever, but I did want something on there that told me how you got your answer. So please remember that in the future. You know, anything you get an answer for, I want some sort of explanation for. Often in this class we do mathematical explanations, but you know, they don't always have to be. That would have been a little phrase, would have been fine on that. Okay. So we good with that? Okay. All right, now what's due on Friday is this review problem, and you know, it's a good review for the exam. We'll go, if you got questions on that exam review, I'll take them on Monday. You don't need to turn it in or anything like that. It's just, or no, yeah, the review you don't. This 3D problem I want you to turn in, but the review problem you don't need to turn in. The test review problems you don't need to turn in. This one problem I do, the 3D review I want you to turn in. There we go. So it's right there. So what we're doing, no it isn't, it's further down. We're gonna make it, we're gonna be all right. So here we go. So that's available in Moodle, okay? It's right there, 3D review problem. I think it's called 2014 or something. Yeah, there we go. So this is the one we were working on in class. It looks like that. So this is basically a lot of 3D things that you can do. So the process on this was to first identify the coordinates on points A, B, and C. So do we have any questions on identifying the coordinates? Appears we're doing all right on that. All right. Okay, now what you want, you've got a force vector there that goes from B to C. So you take RC minus RB, you get a position vector, then you find the magnitude of the vector, and then you divide through by the magnitude, and you get a unit vector, and then you scale that up by 5,200, and you get the force vector. Negative 2581, 1095, 4380. You might have numbers that are slightly different, but they should be close to that. So do we have any questions on that? This solution is also available in Moodle if you want to look at it. It's in there. So you know, you kind of see how all the numbers on this. So we good on the force vector? Have we any questions on that? Not really? Okay. All right, now what you're going to do with that is you're going to find the axial force from B to A, and you're also going to find the moment about A. So you need to work with that vector AB next. So what you want is the position vector, and I went from A to B. Okay, and that's 0.9, negative 4.2, negative 1.6. Are we good with that? Okay, we're good. And that is for the moment, because when you take a moment, you want the length of the vector in your expression, because the length of a wrench affects the moment, right? However, you want a unit vector for the projection. So remember that, okay? Moment requires a position vector, a projection, which is either compression or tension, that requires a unit vector, okay? So I got both the unit vectors from A to B and B to A. All right, so we got the unit vector there. So this first bit here is just coming up with all the stuff we need to put together to get to our answers. How, so we good on that? So what we've got there is criteria for this thing, design standards. We have how much compression it can take, how much tension it can take, how much moment it can take, all right? And shear also. So we have those four things. Now it's only in compression. You can see that it's in compression because we're pulling back towards the wall. There's going to be a component of force going that way, so that will be in compression like that, okay? So the tensile strength, even though it's given, is not required. And keep that in mind. A manufacturer will tell you what their material can do, or this shaft, but they don't know what you're going to use it for. You don't need to use the tension on this because it's not in tension. It's got an axial load in it running down the axis from A to B, but it's compression. It's always one or the other. An object is in one thing or the other. It's not in both, okay? So that thing's in compression. So you're going to compare the compressive force you get to the strength. So to do the compression, you do a dot product. You dot the force vector with the unit vector, and that gets you 3,038 newtons of compression, which, as we were just showing, is kind of a perpendicular type relationship, or it's a right triangle type relationship. That's going like that. So are we good with that? With the dot product getting 3,038, something like that. Okay, you might have got 3,040, that's fine. You might have got something a little different. Now, do use 3 significant figures when you work through things, because if you start using 2, your answers start varying a little too much. So, we're not doing science here. We're not doing chemistry or something where you actually have to track significant figures all the way through. I'm doing 3 significant figures. That's how I do it. Because when I make a building, that's good. Okay, that'll work. Okay. A little different world here. Okay. Now the other thing, so we get on the compression. We doing all right with that? Yes, question.
Tension.
What's that?
The tension is just opposite of that.
Well, there is no tension.
There's no tension.
Right, because that's just being compressed. That bar is being pushed in, so it's in compression. Okay, only. So the tension is irrelevant. So are we good with that? Questions? All right, now at a right angle to that, see this, there's a right triangle relationship here. The shear is at a right angle. So really the shear might be more properly be shown here, but to show that triangle, I'm showing it down where I'm putting it there. So what we have here is a right triangle. We have the force itself is the hypotenuse. The compression then is one of the legs, and at a right angle is the shear. So that's a right triangle. So you can use the theorem of Pythagoras. If you need the magnitude of the shear, you can use theorem of Pythagoras for that. The hypotenuse 5,200 squared minus the compressive leg squared. Take a square root, and that is the shear. Okay.
If I wanted to turn the shear back into a vector, would I take the unit vector of what and multiply it by that number?
Okay, so the question is, how would you handle this in vectors? Now, the first thing I would mention here is you want to read the question first and see what you need to do, okay? Now, on this one, I didn't ask for that. I just want to call that out because sometimes people kind of go on autopilot and do a bunch of stuff. There's no need to do it, because on this, we just looked at magnitudes. Now, if you want that as a vector, if you did, now you don't need it on this one, but if you did, the relationship goes like this. FBC is equal to the vector sum of F compression in this case, because it's a compressive axial force, and plus F shear. So if you want the shear vector, what you do is you got FBC already. You take the magnitude of compression, which is 3,038, and multiply it by the unit vector from B to A. So that would be 3,038 times U from B to A, okay? That would get you the compression vector. Now you got them both, so you can subtract out and get the shear vector. So if you want the shear vector, what you do is you take FBC and subtract off the compression is how you do it. Because you can get FBC, you have to have that to get the compression in the first place, and you can get a compressive vector pretty readily. You just go like that to get the shear.
Do it component-wise.
Yeah, right, yeah, X, Y, and Z, right. Okay, so we good with that? But also, just be sure you're reading things carefully. Don't just go on autopilot, especially on a test. I kind of shorten things up a little bit so you could get it into the allowable time. So, be sure you're reading things and just give me what I asked for, not more. Okay. All right. So we good with that? Okay, the last thing's the moment. Now, what you know, a few things here on the moment. The formula is R crossed with F, not F cross R. It's R cross F, so the R comes first. It is the full position vector. It's not a unit vector because the length of that position vector influences the magnitude of the moment. I think of the position vector as a wrench that goes around the bolt there where you're taking moments about and extends to the force. The length of the wrench matters. The longer the wrench, the bigger the moment, right? So that's why that's not a unit vector. It's a position vector because it reflects how long the wrench is. Right? So that's the reasoning on that. You also have to go RAB crossed with FBC, and the position vector goes from A to B, from the point about which you're taking moments, which I think about as being a bolt, to the force, where your hand is, okay? That's how the wrench is aligned. So both of those mistakes would cause sign errors, okay? So just watch your process and just be sure you're doing that properly. R cross F, and you've got the position vector from the point about which you're taking moments to the force. You have that equation in the lower left-hand corner of your formula sheet, so both the formula for doing a dot product and for doing a cross product are shown there on the formula sheet, okay? So just have a look at this and be sure you know where stuff is and what it looks like. This is what you'll get for the test, okay? I don't do note pages or anything. I just give you a formula sheet is what I do, all right? So we good with that? All right, the other thing too is I had a question about programmable calculators. Basically, the non-programmable calculators that you use on a test are TI 30 and 36s. Okay, the 80s, any of the 80s are programmable, so you can't use those. There's also some others that'll work. There's even a website about this. Let's see, let's go find it. All right, so the TI 30s and 36s, I know a lot of you kind of use TIs a lot. So those are the TIs. There's others too. I've got I don't know what the heck I have. I have a good one, a Casio or something, just a cheap one. Actually, I prefer them to those big calculators too, because how much of that stuff do you actually use on a routine basis? I kind of have a simple calculator that I use to do simple things with. I kind of work my way up as I need to do more complicated things, but whatever. So there we go. So we do the cross product there. Okay, and however you care to do that is fine. The formula, if you need it, is right on the bottom left of the formula sheet. So you just combine the components of R and the components of F, and you get a moment vector. If you need the magnitude, you take the square root of some of the squares. Okay. Questions on that? Okay. So that's a bit of a review there, okay, for the exam, okay. And now there's other things you want to review as well, of course, and I handed out that test review. We'll get to that on Monday if you want to look that over the weekend. Any other questions on this handout? Remember, I do have that, how big can the force go?
Yeah, so we didn't ever...
We're not going to, yeah, some of these I just have them doing on your own. I think it's good, okay. But yeah, if you have any specific questions, I'd take them, but I don't intend to give you too many hints on that. I would say don't do a bunch of calculations on that. For one, it's not worth your time. You got a physics test coming up and all that, so don't ever do it. But the other thing is that doesn't involve a whole lot of calcs on it or anything. There's ways to solve that are pretty straightforward. I don't know. There's different ways to do it. I'll let you figure it out. You see, actually, the truth is I can't figure these things out myself. That's why I don't answer them. So I rely on you guys to find them. You're not buying it? Okay. Well, I don't know. I'm not selling stock, so I guess I don't have to worry if I'm not buying it or not. But anyway, okay. So just give me what you got. Work together, talk to your friends. Don't, I would not burn a whole lot of time on that. You got to prioritize your life, and it's a good thing to be thinking about, but it's not the most important thing. Okay, so we good with that? All right. There we go. So so if you look in Moodle, it might even be under, I can't remember where it is. It's either under the homework downloads or even the test review downloads. It's one place or the other, and there's a key available for this problem if you want to look it over and check your work.